we are Intel Parallel Computing Center. So this is our team, and we collaborate together with Vikram Saratore from Intel and with his team. So actually, I'm going to give you some context. So under this IPCC, we developed very many large-scale deep learning applications. We started with the usual suspects like ImageNet training to thousands of nodes. But then we moved our attention from benchmark use cases like ImageNet training is or ResNet 50 to more real use cases. And these are three of the medical use cases we currently are working on, particularly the left two most, and I'm going to discuss about this one here. The use case comes from a medical center in the Netherlands, very big and important medical center from a city called Nijmegen. It is called the Radboud University Medical Center. And their challenge is in digital histopathology. So this field, digital pathology, is quite important and new for several reasons. So it's the field of analyzing biopsies and seeing at the cell level and tissue and cell level if that tissue is affected by disease such as cancer. So it has a pretty large societal impact, basically. This technique is rather new. This WSI stands for whole slide images. And there are these biopsies that are very large in dimensionality. So you can see the pixel count on that image there. This is like a sample of this kind of images. So it is about 200,000 by 100,000 pixels. Hence, it's called Gigapixel image. So it's quite difficult to analyze patterns in such huge images compared to other types of cats and dogs images you see around. The task here is semantic segmentation. So this means, and classification, but semantic segmentation is the thing that you also see in self-driving cars, where they classify each pixel of a scene, and they say this is a pedestrian, this is a sky, this is a road, and so on. For us, the problem is a bit different, so we want to see each pixel if it represents a diseased tissue or a healthy tissue. And not all hospitals are digitized in this way, so not all hospitals produce this digitized version of their biopsies, but we are in collaboration with some of them that do that. One of them is this Radboud, but also we are in contact with more because we are part of an European collaboration called EXA-mode. That's why I'm acknowledging this project. And this is a much broader project, so it also tries to make sense of the synoptic reports wrote by medical doctors. So basically to also somehow weakly label these very large images. Because you can imagine these images are pretty difficult to label, pixel level labels, since they are so big. And a lab like this produces about 30,000 cases per year. So you can imagine it's a bit of difficult work for pathologists to be very precise in the end diagnosing this. In order to get a glimpse on this problem, we just started with this problem maybe 6 months ago. We tried to tackle some challenges, some competitions. And this is a competition called Camelyon that had an edition in 2016. Then had an edition in 2017, and the edition from 2017 is still ongoing, so people can submit their solutions, basically. It is created by the group from Nijmegen that we are working with, and it has quite high clinical relevance because, of course, it's about breast cancer, this challenge, and of course, 3 million women are diagnosed basically every year in the United States with this affliction. Of course, everybody knows it's a very big issue. So the tasks in this competition are the ones I mentioned. So you have this semantic segmentation where you just want to label every pixel in the image. But you also have classification. So you want to classify the degree to which a tissue is damaged. Because you have this staging in cancer from stage 1 to stage 4. And you want to basically know the degree of problems of this breast cancer metastasis in lymph nodes. Now I'm going to give some description of how our data looks like. Again, a bit different from most image processing or image classification problems, segmentation. You can see that one of these images is about 2 gigabytes in size. And it has multiple levels of downsampling. So this device that generates these digitized versions does also some subsampling in the device itself. So when you see there in the pyramid on the left, 40x, that is the 100,000 by 200,000 pixel image. But then the device also downsamples it to like 10x and 1x. So the 1x is like 40 times more than the 40x. At the moment in this challenge, you have not very many images. You saw that there are thousands and thousands, but why aren't there so many images here? Because it's very, very expensive to label these images. So these are pixel level annotated. But they could only do like 400 of these images coming from 2 Dutch medical centers in 2016. Then they expanded to like 1,000 of these images in 2017. But you can see the data size is also quite large. And as you might know, the dataset size impacts your training algorithm, the execution of your training algorithm, because of all these I/O concerns. When you do distributed training, you cannot have all the data in a node, for example. You cannot just copy it because it's like 2.9 terabytes, or at least not in memory. So then you have to deal with shared parallel file systems such as Lustre, and then you have to deal with like many workers reading from that shared parallel file system these extremely large examples. So it puts a lot of pressure. Here, the types of labels, I said, is lesion level. Here, this is a pixel level annotation. In the 2017, they also have this patient level annotation. So they want to know, they want your model to predict the stage of the cancer that the patient is in. We just looked at lesion level so far. So this is ongoing research. But what we wanted to do, so most people see this big image, most researchers, I mean, see this big image, and then of course they think, okay, we have to use GPUs. GPUs are extremely memory constrained, so then we patch this huge image into patches of 224 by 224 pixels, like our ImageNet models are used to, and then we just estimate the amount of tumors, basically, in each of these patches, and then we do like an aggregate prediction. But we thought, since we're not bound to GPUs, why not use CPU-based system that have loads of memory? That's the whole motivation of this research. And treat a larger patch. Of course, ideally, you would want to do the whole thing end-to-end, 40x. It's not feasible, of course. Our goal now, we didn't reach this goal yet, is to do 1x, the 1x end-to-end. It still involves an image that is, I believe, like 20,000 by 30,000 pixels, so it's still huge. We are not there yet. But we managed to increase the patch level, as you will see in this talk, and I think get some nice results. Besides the obvious problem, that the difficulty of treating such a large-scale problem, this pathology application has another particularity. So all these labs from around the world, in order to obtain this image, they use this procedure that is using some substances, hematoxylin and eosin. So they use this staining to just outline things from the biopsy, like cells and nuclei of cells and the cytoplasm of cells. So this is a cell-level visualization, basically. And because this stain color is varying, not all labs are born the same, basically. So the staining is different. This puts a lot of pressure on the learning algorithm. So in order to make the learning problem easier, our collaborators from Nijmegen also did something called stain normalization. So it's another network that is being part of all this chain. And how they did it is like a generative model, basically, that converts this chromatic distribution of an image to the chromatic distribution of the baseline, of the average image. It's better visualized here. So you would have those kind of source images that have a very different color format, but then you would have this template. You can see the architecture also on the right. It's basically, again, the architecture that makes all these source images appear as they are from the same color distribution. And you can see the target images there. And now the job of the classifier or of the segmentation model is much easier. Still not easy. This is trained beforehand, because this has to be done only once. So you choose your patch size. So you have this big image, you have to patch it. You choose a patch size, and then you have to perform this transformation on those patches. So you do it once per type of experiment, let's call it like this. And it takes about 12 hours, basically, to do this on a single socket, on a dual socket system, on a single node. After doing that, now I'm going to talk about the learning architecture that we use. So we use this DeepLab v3 that is quite famous. It's made by Google. The feature that makes it appropriate for segmentation is exactly the thing on top. The Atros convolution, basically, or dilated convolution, that makes, it's basically like a convolution with, like a sparse convolution, like a convolution with holes. So it makes, you don't have like consecutive filters, one after the other, the filter values, but they are spread out with the ratio you see on top, the rate. So they are spread out by 6 or by 12 or by 18 or so on. Why people do that is because this increases the field of view of your network from the input. So you basically cover a larger field of view in the input, and this is extremely relevant in this kind of application where your input is very, very large. And not only here, also in, again, self-driving, where the images are larger dimensionality than in the ImageNet case, they also use this kind of techniques. Actually, this is the state of the art for image segmentation on the Pascal VOC dataset, Pascal VOC. So basically, this is, and it is an encoder-decoder network. You can see the architecture there, but I am not going to go into the details. But basically, yeah, the encoder encodes into like a latent representation, then the decoder tries to give you the segmentation map. That's the basic idea. The backbone is this exception 65 network. So DeepLab v3 is like a framework. And you can have various backbones. We chose this exception 65. That also proved to be one of the top contenders in this Camelyon challenge. So we thought, okay, let's take the state of the art and basically increase the patch size. That was the idea. The task metrics, so for this semantic segmentation, there are, especially applied to digital histopathology, there are two main metrics. One of them is this Jacquard index. Jacquard index, that is the mean intersection over union. And the intersection over union, it's, yeah, I think the picture says more than 1,000 words. So it's how much your ground truth is intersected basically to the prediction. And the second metric is the binary accuracy for patches. So then you would also have you will have a large number of patches spread from the initial image. And then you would have basically diseased patch or healthy patch. So that's the second metric. And just for completeness, we used sparse categorical cross entropy, basically, for as the loss function. Here I'm going to give some analysis of our training. So let's say 3-4 years ago, when the competition was launched, people were using patches of 224 by 224, exactly ImageNet pre-trained models. And they could do well on GPUs, and it was taking 3 gigabytes of memory, and so on. It was nice. This is for a batch size of 2, by the way. Batch size actually helps with hardware efficiency when you have memory for it, basically. So about 2017, 2018, a group came with the 704 times 704 patching mechanism for this type of images, and they showed significant improvements in the prediction quality. And that's where it stopped, because it kind of, if you have a too small batch size, it's difficult for your algorithm to converge because of several batch normalization issues. So this is just for a batch size of 2. You would think, yeah, but they could use 1,000 by 1,000. Yeah, they could use 1,000 by 1,000. They didn't. We did. So these are actually the results, the memory results we obtained on a relatively large scale run on 48 nodes. And the system was Endeavor. The Endeavor system offered to us by Intel very nicely. And we use this dual socket cascade lake nodes, 24 cores per socket with like 192 gigs of memory. Of course, much more than a GPU could have. So that helped us tremendously. Here, we wanted to see how far we can get with this kind of patching. Like how large can we make these patches? And we used 2 frameworks for that. We have used both PyTorch and TensorFlow to see the memory impact of increasing the patch size. We managed to increase the patch size up to a size of like 6,000 by 6,000. Actually, this is more than 200 gigabytes. There are also other types of nodes in Endeavor that have more memory. The one with 192 gigs we use for our scale-out experiments, I will show later on. But here we wanted just to see the impact of patch size on memory consumption. And as you can see, there's a 32 gig line. This is for a batch size of 1, by the way. So this is a batch size, just one image in the deep learning pipeline, in the deep lab v3 pipeline. And you can see that already at 2000 by 2000, you kind of cross the 32 gig limit, so you cannot do more on accelerated type of devices. You could do if you do model parallelism, if you do other things, but in pure data parallel training, like we normally do, it's not basically possible to do that. And we also projected. So we calculated until 6,000 by 6,000, you see there. But we also projected how much memory we would use if we would have a patch size of around 10,000 by 10,000. You see we go to like about 650 gigabytes of memory. It is still possible on large memory systems. But I think we cannot reach what we wanted, the 1x. So that's, I said before that we want to reach the 1x. That would mean like, I think, 15,000 by 30,000 pixels. Yeah, it's probably going to go into the 1.5 to 2 terabytes range. Yeah. But what is interesting, because, yeah, why did we do this large patch thing? Because in the end, we wanted to reach better accuracy. And in this slide, I show basically the accuracy that is obtained depending on the patch size. So going from 256 by 256, regular size patches that anybody can train on, up to 2000 by 2000 at this moment. And you can see that the improvements are quite significant. By the way, not these results, the results so far here are about memory usage and about how memory usage affects accuracy and so on, but they don't do this stain normalization yet. So this is an optimization from a quality perspective of your prediction that will come on top of this. But already here, you see that, yeah, time per iteration obviously increases as you increase the patch size. But the mean intersection over union also significantly increases. If you see there, you are like from 0.70 something all the way to 0.85, I believe, or almost 0.9. So that's extreme improvement in performance. So, and of course, the number of examples for each patch size varies, obviously, since you have the same input image that you patch in different size patches. But what we also did, and I want to especially thank Gilly from University of Amsterdam that helped us with this chart and analysis. So we also did various size patches for various size zoom levels. So zoom levels are the ones from the pyramid. Actually, it's 4, 3, 2. You would think, why isn't it 1, 2, 3? Because actually, there are 8 zoom levels going from 40x to 1x. I just represent here 3 of them. But now, in this analysis, we pick zoom level 2, 3, and 4. And yeah, what you can see is that the best performance, the best accuracy is obtained by having the largest patch on the largest zoom level. So yeah, this brings us to the idea that probably in the future, we will think of also employing model parallelism to get as large as patch as possible from the large 100K by 200K image. And yeah, that's I think, our next step. Here you would see how prediction looks like. So those are the input images. You see in 224 by 224, predictions are quite coarse. So the white bit is the tumor. We get this input mask. This is the label, the input mask. This is what we predict on the right-hand side. It kind of follows, but you would see that more the following of the mask is more precise for the larger patch size. And what's quite interesting, we are still in talks with the persons from Nijmegen that have created this data set. When we increase the patch, it seems to be actually better than the labeling because we find some new pieces that are not cancerous. And that maybe they thought, OK, why label this as non-cancerous in a sea of cancer, basically? You see from the 1,000 by 1,000 in the right-hand side, rightmost hand side, you see some black spots on the left of the image. And that is not in the label. So this is still like ongoing work with their labelers to see what is this, basically. If we do color normalization, before I showed that we can get almost a 0.9 with a 2K by 2K patch size. However, we also employed the color normalization just for one experiment, this one, of 1K by 1K. We can reach the 0.9 from the 1K by 1K resolution of the patch. So of course, 2K by 2K will probably give us better. And again, you see that that thing there on the right, that black spot that is not in the label. Of course, this all nice, but it takes quite a long time to train on a single node. So we implemented distributed training in a data parallel fashion using Horovod and TensorFlow. And we see quite good scaling efficiency. We can reach about 80% scaling efficiency when going all the way up to 256 nodes. We also get pretty good node efficiency, so hardware efficiency, because we are using 2 workers per node. We bind basically each worker to a CPU socket with its own memory, such that we decrease the NUMA effects. So in the end, it takes about a day to train this algorithm with a patch of a 2K by 2K, I think using 64 nodes. But we have room, because it's difficult to do production experiments on 256 nodes. I mean, yeah, of course, due to the availability on Endeavor, there are a lot of people that want to do experiments. We cannot just monopolize the cluster. But anyway, I want to really give a lot of thanks to the Endeavor support team and Mr. Malik that helped us tremendously doing these experiments. Yeah. However, I think the scaling efficiency is good and is promising for the future. If you combine this with maybe nodes that have 784 gigs or maybe 1.5 terabytes of memory, I think we can really get a patch that is maybe as close as possible to the 1x that we are aiming for. As conclusion, I want to, I think the strongest conclusion is that the patch size and the zoom levels, and basically the amount of information you keep, you don't lose by just upsampling. The amount of information you keep really helps in offering you an improved accuracy of your algorithm. So you don't have to sacrifice this just because you have to use GPUs, I think. That's what we learned from this. And yeah, indeed, it is directly related to the memory footprint, this improved accuracy. But yeah, let's find ways to use large memory footprints, either through model parallelism or through large memory systems. So, and of course, the medical imaging, this really high quality sampling equipment, it's at the moment underutilized because, by deep learning, because of the deficit in memory, let's say like this, or yeah, people are not using large memory for this problem. As future steps, I told you we want to reach the 1x, so to do end-to-end on the full data set of 1x images without doing patches, basically. Patch is full image, 1x. And also, we saw that the zoom level helps, so we also want to do large patches on the 40x. So those are the 2 types of experiments we want to do in the future. So thank you. That was all from my side.